you're better off just writing it, see how it is, see how you do, right? And then go from there. Okay. Let's see here. Okay, so it looks like we're recording. That's on this side. Okay, good. Oops. Business one. Change this little guy. Okay. Now I just want to double check that I'm not on mute. Great. Okay. So this test it's a hard test. Okay. It's a lot of stuff that you cover. It's a lot of multiple choice, which can bring you down pretty quickly, right? And so multiple choice is hard, right? And so there will be multiple choice on the final, okay? But now you've seen some and you kind of know what to expect, right? So like I said, don't worry about this one if it didn't go well, which I'm gonna say it, I don't know, it was better than usual. I know you don't take any pride in that, but oh, funny you should ask. Usually I'm like, I don't care about class averages, but I knew you guys were gonna ask, so I made a little report, and it looks no, they always ask, but it's the only time I'll ever tell you. Yeah. I know people, what was the average? What was the average? Well, you know how to read this. Yeah. Okay. I had to download an Excel file, so I had to import it into R, right? And then I saved the test one data just as test, right? And then I sorted it because there were a couple of zeros, people who didn't write, right? I don't want to have those in the average. I want to pull those out. I don't know how Moodle handles those. Okay, so if you want a job done right, better do it yourself. So then I pulled out the ones with zeros. Here's the distribution of the test marks. Does it look approximately normal? Yeah, ish, right? It's a little skewed. Well, the skew's in the direction of the tail, though. So
I think she said right, as in like in the way we want it to be going. Like,
oh, yeah. So here we've got the majority of our data. It's looking good, right? If you had to kind of eyeball the center, probably around I don't know, 70, right? And then I use the summary command, which you've all seen. So the median was 76% and the mean was 73.5. Are they the same? Not really, right? And then I threw in the standard deviation for good measure. So that's on your Moodle page if you want to have a look. Okay. I obviously can't give you the data, so you can't reproduce it. But I think we all understand that. Okay. So, but I can show you the distribution of the grades. I think it looks pretty good, right? Nothing crazy going on here, okay? So, any questions? Yes. Yes. Yeah, it'll just be added in with the last question. So the last question is out of 8. But your total there will have the bonus as well. And there will always be a bonus. And it's always going to be, I don't know, I like to make the bonuses kind of within reach for everyone. So it's always going to be in the test. Where was it in the test? Very first sentence. Manatees have no natural predators in the wild, but humans have played a large part in making all 3 species at risk of extinction. Harder than it sounds, though, to find it in the test. But I've said that before. This was at UBCO and I said it. And so I had one guy who wrote on the test, oh, it's harder than you think, when he found it. But then one of the tests, he didn't find it. So I was like, well, it is harder than you think. So, okay. So, there you have it. Should we use the mean or the median? Yeah, we could probably use the average, right? So first thing you should ask is not what was the average. Is the average appropriate as a measure of center? Yes, ish. Okay. Applying what we learned. Great, right? Okay. Oh, I'm going to Ottawa, so I'm canceling lab this week. I know, right? I know you're all really bummed about it. Surprise. So, yeah, I think it opens up a lot of Fridays for you guys, so I don't feel bad at all. I do feel bad about forgetting to tell you about it until now. But anyways, I do have a little lab work for you to do. Don't worry, it's not in a lot of R, okay? But I do want you to find a data set. So go online and find a data set that you want to be working with, okay? There's lots of, they don't have to be things that you are very passionate about, just something that, you know, looks reasonable, and the criteria are that it has to have at least 2 numerical variables and at least 1 categorical variable, right? So very simple data set, okay? So instead of lab this week, okay, find a data set online with at least 2 numerical variables and at least 1 categorical variable. Okay, at least. Aim for around 1,000 or more observations. Okay, 500 is okay. So aim for, let's say, at least 500 observations. Obviously, if you find a beautiful data set with 489 observations, that's fine, right? Okay. This may sound like no big deal, okay? But finding the right data set is actually really hard, okay? So, because some of them only have categorical variables or only have numerical variables for whatever reason, okay? I would suggest search for small, simple data sets. Something like that. Okay. Something like that, yeah. Not officially, yeah. But if the one that I got yesterday is right, I'll say that it's early in the, which is good for going away, yeah? Yeah. Like hypothetically on the 12th. Yeah. But you didn't hear it from me, and it's not official. We've had like 3 different dates that they've run through. So you can't hold me to it, but that's the last I heard. Yeah. They're supposed to go out this week, but I'm guessing that they are gonna put it off for a long time because they had a bunch of issues. Like I said, we've gone through, I think, 3 dates before this one. So that's why I'm not putting a lot of stock on this one, but it's supposed to be the last one. So, yeah. Yeah, they should actually be posted middle of October, but yeah, they had some issues this term. But, yeah. So they should be posted this week is what I heard. So just stay tuned, okay? But good for going away. Unless you wanted to go away before finals, but I don't see why. Okay. They can change after they're posted too, yeah. But yeah. Because we're writing at the same time as Stat 124, I don't really see it changing that much because there's so many of you. Oh, hello. Ugh. Shit. Back in action. Okay. Anyways, yeah, so unofficially, you didn't hear from me. I'm not supposed to, obviously. Okay. So this is what you're gonna do instead of labs. So I don't know how to emphasize this. No actual labs this week. No, goodness no. But that one's already been canceled for the whole term. So this one's a bit of a doozy. Okay, yeah. So, yeah, so let's see here. So you could, how do I work this thing? Yeah, yeah. It's out. Yeah. We can handle canceled labs. Small, simple data sets. Where was the one? Oh, this one. So project data sets from France is pretty good. They're in English, but whatever. Okay. I was looking at this one. Okay. They use a different program, but you can just ignore that. Okay. And so it has things like cameras, cars, serials, countries, a lot of government data. I was looking at one cool data set from Alberta. I guess it was like abandoned bank accounts, and the total is like $7 million or something like that. So you can look at the data there. Where the account was last accessed in '86. So abandoned. Okay. So there's tons of cool data out there. That one has tons of variables, right? But it would definitely satisfy what you might want. So you could download that one and just delete all the columns that you don't care about, right? Or pull them all in, okay? Because as you might have guessed, your next task is to bring it into R, right? Bring it into R Studio. Okay? So yeah, so just search small, simple, small because anything I think less than 1 million is considered small. 1 million observations I would call small. So that's why we want to go small. But so small, simple data sets should get you to where you want to be. There's also built-in data sets in R. Okay. Where did I find it? 18 places to find data sets. Okay. We're not the only ones doing this stuff. Oh yeah, so BuzzFeed has some stuff. I think this is where I found Google data sets. Anyways, there's tons of free data. Okay. But, so just see what you can do. I've never had a class do this before, so I'm curious how it works out. Okay. Once you have your data, right, depending on what type of file it is, usually it's going to be a CSV file, right, which we know how to import. Okay. So read.csv, and then you pull it in. Once you have your data, or if it's an Excel file, you know how to read that in too. Import it. Import into a new RMD file. All right, so just start fresh in an RMD file. Okay. And give me the summary of the data set. So include I'm going to say the summary. You don't have to make it up, right? If you're stealing this data, usually they'll have the summary posted. So then you just tell me where you got the data from, right? And then copy and paste the summary. Include where you got the data from and the summary of the variables.
Does where we got the data, could that just be like copying the link?
Oh, totally. Yeah. So just copy the link, where you got the data from. Copy the link. Yeah. Yeah. Yeah, so usually they'll be CSV files because they store the smallest. So people don't usually upload Excel files, but CSV files open up in Excel. Okay, so yeah, so look for CSV files, but even if it's an Excel file, you know how to deal with that, right? You can even use built-in data sets in R. There's lots of built-in data sets in R, okay? You may even use built-in data sets in R. And I was searching, I was doing your homework for you last night. And let's see if I can pull it up on here. Okay, nice. Oh, they just make my life so easy. Okay, so here, okay, it tells you what package it's in. We haven't really looked at that yet. So that would require some research, right? But then here we have all these data sets, right? We looked at the chick weight data that was built in before, right? So it's going to be in this list. This list is huge, okay? And what you're going to want to look for is, has numeric, has to be true. We have to have a numeric variable. We have to have two actually, right? So you might want to check it out. And has character is going to be a categorical variable. And that's the one that you want to look for as well. Okay. You can also look for has logical instead of your categorical variable, right? That's going to be true, false. Those are categories. Okay. Has binary, so 0, 1, right? Basically true, false again. Okay. So those can also take place of your categorical variable. Okay. So here you can just download the CSV file, right? Or just access it built in from R. So maybe I'll put this link. Did I copy it? Copy. See if I can. How can I paste it? Anyways, I guess I'll pull it up. Doesn't really have a name. I'll post the link on Moodle instead. See link on Moodle. Okay. So no labs, but a little bit of Googling for the weekend. Okay. I want have your data ready for next Friday. So you've got some time, which is what date? 2nd? No, that's fine. As long as it satisfies the criteria. Right. And my idea here is that if you bring in the data set, right, then the data set makes more sense to you because you've had to look at it pretty thoroughly, right? You know the variables, right? And so instead of me telling you, go to this variable and pull it out, right, then it'll come more naturally if it's something that you have kind of set out to deal with from the beginning. Okay. So, of course, if you're not sure if a data set is good or bad or whatever, then just send it to me and I can have a look. I can tell you. Okay. But usually it should be pretty good. Okay. Any questions? Okay. So, we're just going to do 3.2. I kind of skipped. It wasn't going to be on the test, so I didn't squeeze it in there. Okay, 3.2 is just evaluating the normal distribution. So evaluating the normal approximation. So in this course, we assume that we have a normal distribution for basically everything, right? And that means that we need another way to make sure that we actually have a normal distribution, right? So what we've been doing is we just make the histogram, and what we usually do anyways, we just make the histogram. Does it look approximately normal? Yeah, great, move on, okay? So since we assume we have a normal distribution, for all of our calculations, in this class, we need another way to make sure that our distribution is normal. We need another way to make sure our distribution is normal. we usually just make a histogram, right? Look at it. Yes, it looks normal, moving on. Okay. We usually make a histogram. And look at it to confirm it follows a normal distribution. Thanks. Oh, awesome, thank you. Okay. So another way that we can test it is using what we call a QQ plot, a quantile plot. Okay. So another test we can use, and there's lots of tests to test normality, right? But we're only going to talk about the QQ plot. So another test we can use is a quantile plot. Or a QQ plot. Okay. So, for example, if we go back to here, right? If we had a mean, right? A mean of 0.7352, let's say that's somewhere, oh, maybe I can't draw on here. Okay, that's fine. So if we had a mean of 0.7352, right, the center would be somewhere around here, right? And the standard deviation I gave you was 0.16-ish, okay? So that's gonna make a normal distribution, right? And so that normal distribution might look something like this, right? Notice how here we have a little bit more than we were expecting, right? And then we have a little bit less than what we were expecting, right? And so what the QQ plot does is it just takes where the theoretical curve would be with that mean and standard deviation, right? So the theoretical would be just kind of this smoothed out line, right? And then it plots it against the actual points, right? Where it's seeing those actual points. And so if they're the same, right, then what you would have is if you drew something like this, where you have the actual points and the theoretical points, right? If they're the same, right? So if your actual points follow a perfectly normal distribution, exactly where the points should be, right? Then you have this perfect line across the diagonal, right? So if the actual data points are plotted against the theoretical, okay, a perfect normal distribution will show a diagonal line, show a straight diagonal line on the QQ plot. So let me just see if I grabbed them. Where's my, there. Okay. So here, right, is what I was trying to show you with that other one, right? So here in the blue bars, you have your actual data points, right? And then we have this theoretical line, right, where it would be if it was perfectly normal, right? And then here we have our QQ plots, right? And so what we see is that we have these points, right? These are male heights in inches, right? And so that's why we don't have a continuous line. That's why there's little steps in there. Okay. But in general, yeah, all these points kind of follow this diagonal line. Okay. And that's how we know that we have a normal distribution. Okay. So, for example, if you had something, now it's kind of hard to see, I guess. If you have something like this, where there's huge curvature either way, right, or it's kind of snaking along, right, then that's kind of indicative of a non-normal distribution, right? I would actually say that these two, they're fine. We can still use them, right? But these ones where we have this clear curvature around the diagonal line, those are bad. Let's see if I can steal this. Okay. Oops. Why not? Come on. I wonder if it has a page break or something that it's trying to avoid. I don't know. Anyways. Make it huge, why not? Right, and so here, this line, that's your theoretical. And these bars are your actual. Looking at this, just the histogram, right? We would say that, yeah, it looks approximately normal. I'll just steal the other examples so you have them in the same place. Okay. And I'll just make a note here. Oops. Hello. Oh, crud. I forgot to charge my pencil. Maybe look at this one. That's more informative. Okay. So QQ plots, we will do them in the lab, right? I'll show you. But spoiler alert, there's just a QQ plot command. And it just does it for you. Okay. Hopefully we're back in action here. Okay. So we would consider these ones approximately normal. That's only because we don't actually know how to deal with anything but a normal distribution in this course, right? So if we have to fake it a little bit, then so be it. Right. But if you've got something like this with huge curvature, can't use it. So, good. All right. That's the end of 3.2. So I didn't sneak it in there. No reason to. Okay. So, let's start section 4.1. 4.1 is the sampling distribution of X bar. X bar, remember, is the sample mean. Okay. So far, we've only been dealing with the distribution of a single variable, right? So just a single observation, right? We have on the assignment, for example, we were talking about salaries. I think it was salaries on the test. I tried to be nice on the test, make it kind of similar to the assignment, right? So we're talking about salaries, right? What's the probability that a single salary is less than this or more than this, right? So now we're going to start talking about the mean of something, right? So because that's what we're usually interested in, right? What's the probability that the average on this test was less than 50%, right? So now we're going to talk about probabilities associated with averages instead of a single observation. Okay. So now we will start talking about how to find averages, or how to find probabilities, probabilities associated with averages instead of single observations. Okay. So up until now, we've only talked about probabilities associated with single observations, right? But now we're going to start talking about probabilities associated with mean observations. Okay? So that means that we need to know how the means are going to be distributed. Okay? And that's where the sampling distribution of X bar comes in. Okay? So we need to know how means, or how the means, are distributed. Okay. Here's a fact that you just have to know, absorb. If X, we've seen this before, follows a normal distribution with a mean mu and a standard deviation sigma, right? So in words, if X follows a normal distribution with a mean mu and standard deviation sigma, right? That's what that shorthand notation is saying. Right? Then as a fact, then X bar follows a normal distribution with the same mean. We'll talk about that. But the standard deviation changes to sigma over root n, where n is the sample size. So then we're saying then X bar follows a normal distribution with a mean mu and standard deviation sigma over root n. So what does that mean? So we've talked about heights, for example, right? If we just take all the heights of people at the college here, right, we know that we would have this variability in our data set, right? From short to really tall, and then most people in some sort of mid-range, right? And so we can kind of imagine our normal distribution, right? The idea here is that if I take a sample, right, so I randomly select a sample of size n from the college here, and I calculate the average, right, and then I throw those people back in, and then I collect another random sample, and I find the average of those guys, right, and I'm constantly recording the averages now, right, in my data set. Then I've got a list of averages now. And so what we're saying is that, well, if I were to make a histogram of those guys, they would also follow a normal distribution, which makes sense, right? Because we're pulling from a normal distribution, right? But they're also going to be centered on the mean, right? If the mean of all the heights is, I don't know, 150 centimeters, let's say, I don't know, something 160, let's do, right? And so, so that's the overall mean, right, for the whole population, mu. Okay. And then I pull a sample. Where do you expect the average of that sample to be around? Probably around 160, give or take, right, but closer to. So what we're saying is that the mean is going to be the same for a single observation and a mean observation, okay? But the standard deviation is going to get smaller for the mean because we expect our means to be closer together, right? Because as we go out and we collect these samples, right, even if there are some really short people, some really tall people in there, right, they're going to get averaged out, and we're all going to hang out around 160 anyways, right? And so the spread for a mean is much less, right? In fact, the spread depends on the sample size, right? So let's write that down. So the spread sigma over root n for a mean observation will be less than the spread, spread sigma for a single observation but also sigma over root n overall, right, is going to decrease as n increases, right? Because the square root of n, that's just kind of scaling down our n, right? But as n increases, the square root of n also increases, right? So that means that we're going to be dividing by a larger number. So overall, we get a smaller value, right? So sigma over root n will decrease as n increases. So that's why we want to have larger samples, right? Because it means a more stable and less spread for our average, right? A more robust average, okay? So that's why we want large sample sizes, right? Because we will have less spread in the distribution of our mean. So we'll have a more robust estimate for the mean, which means we will have a more robust, thank you. Oh, you can keep this. Yeah. A more robust estimate for X bar. Some terminology, okay. Sigma over root n is essentially the standard deviation of X bar, right? So it's the standard deviation of X bar, but do you see the problem in having sigma in there? Sigma is the standard deviation of a single observation, right? So what we end up saying is that the standard deviation of X bar is the standard deviation of a single observation over root n. That's kind of messy, right? So instead, we call it the standard error. Okay. So the standard error is sigma over root n. Okay. SE is standard error, sigma over root n. And it's just so that we can differentiate between sigma, right, is the standard deviation of a single observation, and sigma over root n, we'll just call that the standard error, and that's for a mean observation. Okay. So, any questions so far? Okay. So, if we know that X bar follows a normal distribution, and we know the mean and we know the standard error, right, or the standard deviation, we can still calculate z-scores, right, to find the probabilities. Right? So since we know X bar follows a normal distribution, and the mean, and we know the mean, and standard error, right, we can still use z-scores to find probabilities. So what we've seen, right, in 3.1, we saw a single observation. Right? which we said X follows a normal distribution with a mean, mu, standard deviation, sigma. Right? So we know that. And so we use Z equals X minus mu over sigma. Right? And that's on your formula sheet, right? In section 3.1, if X follows a normal distribution with mean, mu, and standard deviation, sigma, then use Z, right, where Z is X minus mu over sigma, right? So now, in section 4.1, we're talking about a mean observation. And we know that X bar follows a normal distribution with a mean, mu, and a standard deviation, sigma over root n. So if we're going to use Z, well, so Z must be X bar, right? Because here, this guy went here, this guy went here, and this guy went here. So same idea, right? X bar goes here. Minus mu over sigma over root n. Right. So it has the exact same setup. The only thing that changes is that now we're talking about a mean, and so we have to account for n. Okay. A single observation is just the sample size of 1, right? So what if you plugged in n equals 1 in here? The square root of 1 is 1. Sigma over 1 is just sigma. So then you're back to just X minus mu over sigma. Right? So they're the same. Okay. And so this 4.1 section is, of course, on your formula sheet in section 4.1, sampling distribution of X1, X bar. Okay. Yeah, so it'll depend on the question, right? If you want to know something about a single observation, then you've just got X. If you want to know something about a mean, right, so I'll say, what's the probability that the mean is less than 400 or whatever, right? Then you have to use X bar. Yeah, but the idea stays the same. In fact, the questions even start the same. Okay, so 4.1 type of questions just continue from 3.1 type of questions. Just continue from 3.1 type of questions. Okay. So in its most basic form, right, 3.1 type questions, we said something follows a normal distribution with a mean, mu, and a standard deviation, sigma. Right? So how these questions are going to be laid out is that that's all you get in the beginning, right? So it'll start with something follows a normal distribution with the mean, mu, and standard deviation, sigma. Just like assignment. Okay. So earn a mean salary of 30,000 with a standard deviation of 4,000, assume that the distribution of salaries is normal. Right, so it follows a normal distribution with a mean of 30,000 and a standard deviation of 4,000. Okay. Part A would be find the probability associated with a single observation. Right. Find the probability of a single observation. Okay. So question, the long answer, the last long answer question on the test or assignment 3, right? Something like that. So those types of questions, those are all for single observations. So see test 1, long answer number 2, and assignment 3, right? For questions about a single observation. Then we just build on this, so we don't need another blurb. I just say, okay, you collect a random sample of size n. Okay. You collect a random sample of size n. And usually the first thing I'll ask is, what is the sampling distribution of the mean? What is the sampling distribution of the mean? Oops. This is where you're just going to take, right, the sampling distribution of the mean is x bar follows a normal distribution with a mean mu, standard deviation sigma over root n. You're going to take the mean from the blurb, right, that you already know, the standard deviation from the blurb that you already know, and then put it over the square root of whatever sample size I told you to take. Right. So you're just filling in that line, and that's all you do for that. Okay. That is the sampling distribution of x bar. Okay. Then, what is the probability that the mean is less than blank, for example? Right. Thing here is that we're talking about the mean. So now you're going to use z equals x bar minus mu over sigma over root n instead for your calculations. But the idea stays the same, right? You want to calculate the z score for that mean observation, use that z score in table C to find the probability. Right? So you were all working on assignment 3, so let's just steal assignment 3. Would you rather look at assignment 3 or the test? You just worked on assignment 3, handed in, but I guess you have the test in front of you. Rather assignment 3? Doesn't matter to me. Let's continue assignment 3. So for example, continuing
from assignment 3? Question 1, I guess. So the question says, sociology students, and this one is the one I think is so funny, sociology graduates, upon entering the workforce, earn a mean salary of $30,000 with a standard deviation of $4,000. Assume that the distribution of salaries is normal. Yeah. So you did parts A, B, C, D, E, F. So we'll start on G. Did A to F in assignment. Part G. You select a random sample of 50 salaries. Or you collect a random sample of 50 salaries. What is the sampling distribution? What is the sampling distribution of the mean X bar? Usually I try to put the mean comma X bar just so it triggers your, okay, the sampling distribution of X bar. I know what that is, right? The sampling distribution of X bar follows a normal distribution with a mean mu, standard deviation sigma over root n. I'll just do the blank one from your formula sheet. That's fine. And then I'll fill it in with my values. Okay. So X bar follows a normal distribution with a mean of 30,000 and a standard deviation of 4,000 divided by the square root of 50, right? My sample size is 50, so that's what I plug in. And that's it. You did the question. Even if you just went to the second line, that's fine. Okay. But then you're done. Now, H. Let's see here. Let's do this one because it was, so you did the probability that it's over 27,000 in part B on the assignment. Okay. Let's find the probability that the average is over 27,000. Okay. So what is the probability that the mean salary, or that a mean salary is over 27,000. So if we draw our normal distribution, right, it's going to stay the same. We know it follows a normal distribution and we're still centered on 30,000. But now we have sigma over root n is 4,000 over the square root of 50. So 27,000 somewhere here. So we want to know what's the probability of being up above there. So if we want to find probabilities, we first have to find the z-score, right? So now we can calculate z equals x bar minus mu over sigma over root n. So now we want to know what's the probability that the mean salary is over 27,000, right? So our x bar is 27,000 minus 30,000 all over 4,000 over the square root of 50. Deal with the numerator and denominator separately, right? Simplify them. So I've got a kind of a crappy calculator here. So I find the square root of 50 and then I take 4,000 divided by that. So I have what, negative 3,000 over 0.8888. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 9, 4, 4, 6. 27,000 minus 30,000 just to check. Divided by that guy. Now I'm at negative 3 point. What the? All right. 3,000. Did I do that right? Oh, I didn't. I didn't. Operator error. Divided by 565.6854249. That looks better. Negative 5.3033000859. Whereas for a single observation, right, we had 27,000 minus 30,000. Oops. Divided by 4,000. Right. Versus for a single salary, Z was just negative 0.75. Right. So when the mean, right, when we're talking about 27,000 for the mean, right, then if we look at our Z distribution here, Z is centered on 0. And our 27,000 is somewhere way out here at negative 5.303. If you try to use your table, it doesn't even go that far. Because first you have to find the area in the tail, right? The area in the tail, all we can say is that at some point, I'll just put here, negative 3.291, right? Here, the area in the tail is 0.0005. So the probability of a salary less than 27,000, a mean salary less than 27,000, is less than 0.0005. So we know the probability of a mean salary less than 27,000 is less than 0.0005. So the probability above is going to be approximately 1. Right? We're so far out into the tail, negative 5. The probability of being above that is approximately 1. So the probability of a salary, or of a mean salary, that's important, more than 27,000 is approximately 1. Nice. All right. Time. Sorry to keep you guys. Yeah. See you on Monday, I guess. Oh yeah, I kind of forgot about the labs, but I'll mark them this week sometime.
And for the other the sample set, do you just like email you like an HTML file?
If you don't need me to look at it, then I don't have to see it. Then just have it ready. You too. Just have it ready for Friday. But if you want me to look at it, then yeah, maybe send me the
Ready for this Friday or next Friday?
next Friday.
Okay.
Yeah.